Hello, everybody. Welcome to this last talk of today. So my name is Nikolai Kosmatov. I am a researcher at CA-List, a research institute in France, and I work at the Software Safety and Security Lab of CA-List. We develop tools for software verification and validation, in particular for testing, for static analysis. Maybe you know the tool Pharmacy, which offers several static analysis plugins and also dynamic analysis plugins. And in this talk, I will talk about test coverage criteria, and in particular about some advanced test coverage criteria and a systematic, universal, unified approach to specification, measuring, covering test objectives, and detecting or unmasking infeasible test objectives. So this work is done in the context of white box testing. White box testing, a very simple view of white box testing can be shown by this picture. Basically, we generate a test input, we run it, check for errors, we estimate coverage. If the coverage is sufficient, we stop. Otherwise, we continue. So we consider the program. We have its specification. We run a test case and observe it. If there is a bug, it is detected and reported. We check the coverage. If the coverage is sufficient, that's OK. Otherwise, we generate a new input and continue the process. So rigorous structural unit testing is useful, of course, in various contexts, for instance, for critical code, for embedded code, where coverage is important. So the framework is white box software testing, and the goal is automating test case generation and coverage measurements. In this context, an important role is played by coverage criteria. A coverage criterion describes objectives that must be fulfilled by a test suite. Such a criterion guides test automation, and it can be also part of industrial requirements, certification standards, such as the avionics standard, for instance, DO 178, and so on. It happens that there are a lot of coverage criteria in the literature. The famous Aman and Offutt book on testing describes 28 coverage criteria. But in practice, in the existing testing tools, very few criteria are supported. If we have a look into some existing tools, here is a selection of tools, we will see that only some criteria are supported by some tools, and most of the others are supported by no tools. The criteria are thus very dissimilar basis for automation, and they are restricted only to small subsets of the support is restricted to small subsets of criteria. And the extension of tools to different criteria is very complex. So how we can bridge the gap between different criteria and testing tools? So the main ingredients of this talk will be the specification mechanism that is called labels, which allows to express several criteria in a generic, universal way, and provides a semantic view with a formal treatment for this criteria. A new efficient test generation technique that we call DSE star, which is based on dynamic symbolic execution and which allows to cover the criteria expressed in labels in an efficient way. And we also describe an efficient technique for detection of infeasible objectives using static analysis. We show an implementation of all those techniques in a testing toolset based on Pharmacy and Pathcrawler. And finally, a recent extension of the label specification mechanism to more complex criteria, including in particular MCDC. So the goals, as I said, are how to specify criteria, how to measure the coverage of an existing tool suite, how to cover test objectives, and to unmask infeasible test objectives. So, labels. What are labels? Labels are basically a very simple, almost obvious mechanism to describe test objectives. For instance, here, to cover both cases for this condition, x equal to y at this point, I can simply insert label 1, saying that at this point, some of my test cases must reach this point and satisfy this condition. And another label says that I also have to reach this point and satisfy this condition. And in this case, I will have the coverage of this first condition. Both cases, the condition is true and the condition is false, will be covered. More formally, we can say that a label is a pair, location and predicate, and the goal is to reach this location and to satisfy the predicate. So we say that a test covers a label if the execution of the program on some test datum t reaches location log and satisfies the predicate. We can thus introduce a new criterion that will be coverage of such labels, which requires to cover all labels in this program. So for instance, for this program, I will cover both labels if I will have one test case reaching this point with x equals to y, and one test case reaching this point with x different from y. So now what is the link between this simple mechanism for specification of test objectives with the existing test coverage criteria in the literature? The link is very simple. We say that a criterion C can be simulated by labels for any program P if, after adding appropriate labels into this program, we are able to have the following equivalence. A test suite covers the criterion C if and only if this test suite covers all labels we added into the program. Let me give you a few examples. So here, for instance, how can I simulate condition coverage for this program fragment? It is sufficient to add these four labels: first condition true, first condition false, second condition true, second condition false. And in this case, a test suite covers all statements, all conditions in this first program, if and only if it covers all labels in this second program. Right? Because covering a condition, it is exactly making it true once and making it false at least once, and so on. So if we insert such labels for all conditions on our program, we will get an equivalent representation of the condition coverage criteria for this program using labels. It can be very similar for decisions. So the decision coverage criteria means that we have to cover at least once each decision. So they cover the then branch and the else branch of each conditional at least once. So in this case, we add just two labels in this way. And again, my test suite will cover all decisions in this program, if and only if it will cover all labels in this program. Similarly, I can cover multiple condition coverage, which means all combinations of conditions by adding labels: first condition true, second condition true, first condition true, second condition false, first condition false, second condition true, and both false. I can also express function coverage in the same way, and so on. So overall, we can show the following theorems: that instruction coverage, decision coverage, function coverage, condition coverage, multiple condition coverage, and also some other criteria like input domain partition, runtime errors can be expressed using labels. Interestingly, there are also other criteria such as weak mutations, which can be expressed using labels as well. Weak mutations, if you don't know, means that we modify a program at some point by introducing a mutation and compare the execution of the mutated program with the original program right after this point and check if there is a difference. So labels can express most criteria, and they can also provide a simple and efficient algorithm to measure the coverage. I will not give you all the details, but basically, since all criteria are encoded in the same, all objectives are encoded in the same program, it is sufficient to check for all test objectives by running this program once and on an instrumented version of this program and check all of them at the same time. It is not obvious for mutations where usually to know if a mutant is covered or not, people run separately each mutant, and it takes a lot of time. Well, that's quite a simple and obvious mechanism to express different criteria, but why it is so interesting? It is possible to support different criteria in a universal, unified way thanks to this mechanism. So we implemented a tool set, LTest, based on top of Pharmacy, the software verification program, which allows to support different services around testing. And in particular, given a program and a criterion, a user can run label annotation, insert labels, and produce an annotated program. For an existing test suite, the user can also execute tests and measure the coverage, have a coverage report. Of course, it is possible to generate tests and find test cases or detect uncoverable test objectives. And what is interesting is that all supported criteria are treated in a unified way, and it is rather easy to add other criteria. But, well, it is nice to express criteria and to measure the coverage, but of course the most interesting thing is how to cover test objectives, how to produce test cases in this case. And I would like to give you a few insights about how labels can be efficiently supported by test generation techniques. And I will use dynamic symbolic execution, which is quite efficient test generation technique, which is very powerful. There are lots of tools which exist, in particular Dart, Qt, Pathcrawler, XSH, Bex, CLI. And one of the most successful efforts in using this technique was in Microsoft, where the Sage tool was run on hundreds of computers in parallel to detect errors. So it is based on symbolic execution, which is an old idea. Maybe I will not detail it now. And it also integrates a dynamic part so that the program is executed in parallel symbolically and concretely to produce a very efficient test generation technique. Maybe I will give you just an intuition how it works. So here is a more formal presentation, but basically a test case is generated, it is executed, then we just can try another path. Here it is shown in a depth-first search. We try to cover it. Then we go for another path. Each time to generate a test case for each path, we construct what is called the path condition, the conditions which will ensure that we execute this program path in the program, and we continue the process until we cover all paths with a limited length. So, how we can adapt this rather costly technique to labels? So the challenge is how to extend dynamic symbolic execution to a large class of coverage criteria. The existing efforts in this direction appear to be rather costly because they lead to an exponential explosion of the search space where the overhead is more than 272, and these solutions are very implementation-centric and not really unified. So let me give you some insights how we can provide efficient test generation techniques for labels. One naive, obvious solution would be to say, okay, I have a label between two instructions, 1 and 2, and I can simply instrument my program by inserting a condition if P and Now I have 2 additional branches between these statements, and I cover the label L if and only if I cover the true branch in this new program. Okay, indeed, it will work. It provides a sound and complete instrumentation with respect to label coverage. But what happens if I have a sequence of n instructions and n labels between them? In this case, instead of 1 program path, I will finish with 2 to the nth paths. So the new program, the new instrumented program that I call here direct instrumentation P prime, it is not good enough. It will lead to an exponential increase of the search space for my dynamic symbolic execution, and it will be, of course, very costly. It is not all. Paths are also more complex in P prime. At each label, I will cumulate the conditions in the program with the conditions of the labels, with the predicates of the labels, with the predicates P1, P2, and so on, Pn. So my path condition will be more complicated. It will include all conditions of the labels. What can we do about that? The idea is to produce a more efficient and optimized version of the dynamic symbolic execution, which is based on another tight instrumentation P prime, which totally prevents complexification, and which also uses another optimization, which is iterative label detection, which discards redundant paths to make it even more efficient. So how it works? Instead of using the instrumentation I showed before, what we can do is that we basically instrument the program in this way. We can replace the label by the non-deterministic operator non-det, and if non-det says yes, true, we go to checking the label predicates and exiting the program. Otherwise, we continue the program execution without checking the predicate of the label. And in this case, again, if we use dynamic symbolic execution on this new program, and if we cover all program paths in this program, we will be able to cover the label when we will cover this branch, this part which exits here. Why it is interesting? It is interesting because if we compare both, we will see that in this first obvious instrumentation we saw before, where we had an exponential increase in the number of paths, in the new version we have only n additional paths for the path we consider here. So what happens is that we do not have an exponential increase, we have only a linear increase of the number of paths in this new instrumentation of the program. Moreover, in this case, we said that we had a combination of conditions on each path. We had a combination of P1, P2, Pn, and so on, which remained on the path and which complicated test generation. In this second way, we see that when we consider a predicate, the predicate of a label, we exit immediately. And if we continue program execution, we do not consider the label anymore. So we don't have any additional constraint. It shows why this new instrumentation is basically very efficient in theory, and we will see that it is also more efficient in practice. And if we consider this new instrumentation, we will go much faster, because in this way we will be able to consider the different paths of the program much more efficiently. So this new instrumentation has only a linear increase of the number of paths, and the paths are simpler. Each path covers at most one label. And this solution also provides a sound and complete instrumentation with respect to the label coverage without any complexification of the search space. Okay, that is nice, but the problem is that sometimes we have the same labels, the same paths in a loop or in a function that we call several times, and in this case we can still try to cover again and again the same test objective. We can also propose another optimization for this, and the optimization that I call iterative label deletion, where we can iteratively delete labels, ignore labels as soon as they are covered. Basically, if I explain only the main idea of that, that would be something like this. We go to check in a label only if this non-det operator says yes, and if the label is still uncovered. You may wonder, what is non-det? What is this non-det operator? It can be a non-det operator which is provided by a test generation tool, or it can be simply simulated by an additional symbolic input in the program or an array of inputs, so that for each place where we use a non-det, we have we try a value true and a value false each time. And to combine both, we can basically use dynamic symbolic execution on the tight instrumentation P prime. We can run a test datum concretely on the direct instrumentation P prime in order to detect if the test datum we generated covers by chance other labels which are on the same paths. And we accumulate all coverage information in a database, and they continue this process iteratively until we cover everything. So, if we sum up, we have a tight instrumentation technique which totally prevents complexification during dynamic symbolic execution. We have an iterative label deletion technique which discards redundant paths, and both techniques can be implemented in black box. So, experimental results that I don't show here show that it leads to a very important increase in performances for test generation. Instead of 272 times slowdown overhead we showed before, we can finish with 7 times overhead, which is of course much more efficient with respect to the basic version of dynamic symbolic execution, which doesn't target a specific criteria. That is of course nice, but we also want to detect infeasible test objectives. The problem of structural coverage criteria is that they are structural. They are structural, so they do not take into account the semantics of the problem, and many of them are in fact infeasible. They lead to wasting the test generation effort, they lead to imprecise coverage ratios, and the problem is how to detect such infeasible test objectives early in order to avoid this waste of effort. It is particularly painful in aeronautics, where some criteria such as decisions, conditions, MCDC are used, and we try to cover them while sometimes it is not possible to cover them. So what we would like to use is, what we would like to have is to have an automatic detection technique for uncoverable test objectives. A sound method applicable to a large class of criteria with a strong detection power, a reasonable speed, and if possible, that would rely on existing verification technique. I will show it on a small example, but before giving you the example, what is the main idea of the technique? The main idea is that a label cover the predicate P at location lock is uncoverable if and only if the assertion that is negation of P, assert negation of P at location lock is always valid. So we can basically reduce the problem of detecting uncoverable labels to proving that some assertions with the negated predicate P are always valid. So let me show how it works on this example. So here in the main function, I just use some predicate, some functions that create a context I would like to have. I suppose that this function returns some non-deterministic value between 0 and 20, and here this function returns a non-deterministic value between 0 and 1000. And after this initialization, I call the function g of x and a, so that basically x can be only between 0 and 1000, and a can be only between 0 and 20. And then I have this simple program, just to give you an example, where I have a conditional statement. If x plus a greater or equal to x, then the resulting value res is 1, otherwise it is 0. Of course, for those values, a and x, x plus a will be always greater or equal to x, and the only possible outcome will be res equal to 1. And suppose that, for example, I have two labels. Here I want to cover the situation where res is equal to 0, and here I would like to cover the situation when res is equal to 2. Can I use some existing static analysis techniques to show that both are actually impossible? To try that, I will use two techniques: value analysis based on abstract interpretation and weakest precondition calculus, which is WP, which are available in a platform like Pharmacy, and that can be used for this goal. So here are some characteristics of these tools that I will not detail. What is interesting here is if I translate the assertions into the labels into assertions, I will get the labels like these ones: res different from 0, res different from 2. And if I run value analysis or WP, weakest precondition calculus, they will be both able to detect that the second one is valid, so the second label is impossible to cover. But unfortunately for the first one, they will not be able to show that it is uncoverable. Why? Because value analysis will not be able to deal well with relational conditions like this one, while weakest precondition will not be able to deduce that x and a are only in these intervals in this case. So what one can do in this way is to combine both and to, let me show it here, and to use value analysis first to compute the values of the possible values of each variable at each program point, and to insert the domains of the variables here at the entry of the function, and then to run WP, then which will be able then to deduce that, of course, if a is between 0 and 20 and x is between 0 and 1000 res, then this condition is always true, and it will be able to deduce that this variable is always different from 0 at this place. So we will be able to deduce that both labels are actually uncoverable. The results show that this combination of analysis techniques is very efficient. It has a detection power of 95%, a good detection speed, and so on. More recently, we worked with other sources of polluting test objectives, which are not only infeasible objectives, but also duplicate test objectives, subsumed test objectives, where one objective always implies another one, and they can be also detected using static analysis, using WP-based algorithms. So thanks to these techniques, we can construct an overall all-in-one solution where, given a program and a criterion, we can generate labels, detect uncoverable objectives, take into account which objectives are uncoverable when we generate test cases, or complete an existing test suite, and of course execute an existing test suite, or generate test cases for a given criterion. So I think I don't have so much time for the last part, but what I wanted to show is that all these criteria based on labels were able to express some of the criteria, but not all of them. What do we need to express other things, other criteria? For instance, in this criterion call coverage, I have to cover the calls to G, but at least one of them. So I would like to express something like, at location 1, I would like to cover this call or this call. So I need disjunction. In this case, in all depth criterion, in the all depth criterion, I would like to express the paths from a definition of a variable to at least one of its uses. So I need to express sequences of things, sequences of events on my path. And finally, in the MCDC criterion, if you don't know, this criterion requires to cover situations where you have the same value, you have two test cases where all conditions are the same, and only one condition changes, and the decision changes as well. So this is a criterion which compares several executions for several test cases, and you must relate several executions of several test cases between them. And for that, we need to talk about several test cases. And all that can be expressed in the most recently proposed hyperlabel specification language, which adds sequences, guards, conjunctions, disjunctions, bindings, and which allows to express, with this semantics, allows to express what does it mean to cover this location or this location, or what does it mean to cover paths from passing from log 1 then to log 2, or from log 1 then to log 3, and there is also a way to define MCDC. So there are some most recent extensions which allow us to express very, very powerful criteria, which can be represented by this taxonomy of criteria with several directions, criteria needing disjunction, needing hyperproperties, or needing safety, or sequences of events. So, thanks to this extension, almost all criteria of the book I showed you before, 27 out of 28, can be expressed in hyperlabels. But this new extension is not yet fully supported, and of course, the future work will be to support efficiently this solution, to provide efficient techniques for, as I show here, an efficient dedicated support of hyperlabels for test generation, for detection of uncoverable hyperlabels, and on developing the emerging interest for this technology and industry. So what I showed you is a generic specification mechanism to express different advanced coverage criteria, a test generation technique which shows how we can efficiently cover them, an efficient technique to detect infeasible objectives expressed in this mechanism, an implementation of all these techniques, and a recent extension of labels to hyperlabels, which allow us to specify, measure, cover, and unmask test objectives. Thank you. Are there any questions?
Thanks for presentation. Have you information about vector cast?
About what?
Vector cast. I show product as Parasoft, and we want to use vector CAS. I have information and coverage criteria on this product.
I don't see. Can you explain again what is the question? Можно по-русски. В каком смысле информация?
По парасофту у вас есть по критериям.
В смысле информация по возможностям поддерживаемых критериев. В этом смысле? Понятно. Мы взяли инструменты, которые были в одном из недавних обзоров, и здесь, конечно, частичный список. У меня под рукой нет информации, какие критерии там поддерживаются, но я сильно подозреваю, что далеко не все из этих, но информации точно у меня нет.
Разработка, она актуальна именно для юнит-тестов, как я понимаю?
Да, она актуальна для юнит-тестирования, и большинство модулей того, что я показал, являются открытыми, кроме одного.
Я правильно понимаю, что эту программу можно использовать, ну то есть она бесплатная, да, или как?
Большинство модулей бесплатные, кроме одного. Один только не является открытым.
Какой модуль?
Модуль генерирования тестов является закрытым.
То есть, получается, сгенерить тесты не получится, да? Он что, он найдет
сгенерировать тесты можно, но нужно попросить лицензию.
Ну понятно, я имею в виду...
Нельзя скачать и сразу сгенерировать. Можно...
Тест-кейсы, да? То есть он сгенерирует, да? Или... Что имеется в виду? То есть он сгенерирует тест-кейсы, да?
Открытые модули, которые я показал,
Или открытые модули?
Являются модули для определения вот этих вот labels, для измерения покрытия.
Покажет нам, что не покрыто? Он покажет?
Он покажет, что не покрыто, он покажет, какие невозможно покрыть. Единственное, чего не хватает, это вот этот модуль, и к ним нужно, по поводу него нужно обращаться за лицензией, потому что он недоступен в открытой форме. Пока это поддерживает только C-программы. Их можно автоматически сгенерировать для выбранного критерия, да.
Еще вопросы?
Они квалифицировались на авиационку? На авиационку не квалифицировались?
Нет, они не квалифицировались формально, но в процессе использования в индустрии, в процессе...
Qualification kit у них уже есть или они в процессе еще получения его?
Qualification в каком смысле? Какую-то конкретную квалификацию вы имеете в виду? 170.
Авиационка.
Авиационка. Они в процессе изучения, но пока что в авиационной промышленности автоматическое тестирование не вошло еще в общую практику, во всяком случае среди наших партнеров.
Microsoft они предлагают за определенную плату qualification kit, если ты хочешь участвовать в разработке. Microsoft они предлагают, как собственно и Vector CAS тоже, за определенную цену qualification kit. Если ты хочешь участвовать по DALU-A, вот у них есть что-то подобное?
В этом варианте пока еще нет, но я надеюсь, что будет.
Так, еще вопросы? Все?
Спасибо.